The last time we talked about chemical potential. We can consider a situation where we have two systems, both in contact with a reservoir at temperature tau. And we establish diffusive contact between the two systems, which means that particles can pass from system 1 to system 2 or in the other direction. So the total number of particles is conserved, n1 plus n2, but particles can flow from one system to the other. And now if we want to find the most probable configuration, the most probable way of sharing the particle number between the two systems, when the temperature is fixed by the reservoir to be tau, then we should minimize free energy. Remember, e to the minus free energy divided by tau is e to the sigma, the degeneracy. Sigma is the entropy. E to the minus u over tau, the Boltzmann factor. If the system borrows energy u, then it reduces the reservoir's degeneracy by this amount. This is the degeneracy of the system. And so at temperature tau, the free energy will be minimized when the energy that the reservoir loans to the system maximizes the probability of the configuration. And so if we choose u so that this quantity is maximal, then the free energy becomes a function of tau. So we consider the free energy to be a function of temperature, volume, and number of particles. And if we keep the volume of system 1 fixed and the volume of system 2 fixed, the total free energy is F1, which depends on the temperature, V1 and N1, plus F2, which depends on temperature, volume of 2, and N2. When the particle number in system 1 changes, when we're in the most probable configuration, dF should be equal to 0. In general, we'll have partial derivative of F1 with respect to N1 with temperature and volume fixed times dN1 plus partial derivative of free energy of system 2 with respect to N2, temperature and volume fixed, dN2. dN2 is equal to minus dN1, since the total particle number is fixed. We can define the derivative of free energy with respect to particle number with temperature and volume fixed as the chemical potential. This is the chemical potential of system 1. This is the chemical potential of system 2. The first order change in the free energy when N1 changes is then the difference, mu1 minus mu2, dN1. So in order to seek out a more probable configuration, which means a lower value of the free energy, to seek the most probable configuration, particle number flows from the higher chemical potential and toward the lower one. So if mu1 in particular is larger than mu2, then to make the free energy lower, which means a more probable configuration, dN1 should be negative. And if mu2 is higher, then dN1 should be positive. And the flow will continue until diffusive equilibrium is established, which means the chemical potentials are equal. And there's no free energy gain to first order in having particle number flow in either direction. And we computed, as an example, the chemical potential for an ideal gas in the classical regime. finding the chemical potential as temperature times natural logarithm of concentration divided by quantum concentration. Classical regime means concentration is small compared to quantum concentration. So what it means is that when you establish diffusive contact, if you have two ideal gases, both with the same species, remember the quantum concentration depends on the mass, then particle number will want to flow from the higher concentration gas to the lower concentration gas until the concentrations are equal. And then the overall system is in equilibrium and has its most probable configuration. There are other ways we could define the chemical potential in terms of other thermodynamic variables. Again, remembering that by free energy we mean U minus tau sigma, which becomes a function of tau when we choose U in order to minimize the free energy. If we consider the first order change in the free energy, we can write it as, let's imagine the volume is fixed, but the entropy can be changing. So it's the derivative of energy with respect to entropy with particle number fixed times the change in the entropy, plus derivative of energy with respect to particle number with entropy fixed times change in particle number, then minus tau d sigma minus sigma d tau from the first order variation of the minus tau sigma term. But now, if we consider the situation we were just discussing in which the temperature is fixed because the system's in contact with the reservoir, then this is 0 because we have constant temperature. And because the system's in contact with the reservoir, what happens to minimize the free energy is that the system comes to temperature equilibrium with the reservoir, which means that du d sigma is equal to temperature. So this first order change and this one just cancel one another. So when if we keep the temperature fixed and we change the particle number, the change in the free energy is the same thing as partial derivative of energy with respect to particle number with entropy fixed times the change in the particle number. So since dF dN with tau and volume fixed is defined as chemical potential, we can equivalently say chemical potential is derivative of energy with respect to particle number with entropy fixed. So we can generalize the thermodynamic identity that we wrote down before, which describes the first order change in energy, entropy, and volume, how they're related. Before we said the first order change in the energy can be written as tau d sigma minus p dV. That's right when the particle number is fixed, but if we change the particle number as well, so now we're regarding the internal energy as a function of the entropy and the volume and the particle number, then we can add plus mu dN. Of course, we can also think of the entropy as being a function of energy, volume, and particle number. Write this as d sigma, and put the other stuff on the other side and divide by tau. So it's equal to du over tau plus p over tau dV minus mu over tau dN. That's supposed to be a tau. So yet another way of defining chemical potential is we can consider the partial derivative of entropy with respect to particle number, this time with energy and volume fixed, and that's equal to minus mu over tau. Okay? Okay. So now what I'd like to do is let's generalize to the case where we have both diffusive and thermal contact, our earlier discussion of a system in contact with a reservoir. Now, the system isn't necessarily large. It could be a small system, but it's in contact with a reservoir. And the reservoir is big. And really what big means is that the reservoir can give up a little energy to the system or a little bit of particle number to the system without the reservoir's temperature or chemical potential changing. So now we'll imagine the system is in thermal and diffusive contact. With reservoir so the reservoir has temperature tau and chemical potential of mu, which we can consider to be constant. So now the system is going to try to find the most probable configuration. Well, the system and reservoir are going to try to find their most probable joint configuration, right? So that is, we want the product of the system degeneracy and the reservoir degeneracy to be as large as possible. Well, you remember what happened in the case where we just had thermal contact. For system state, with energy epsilon, the probability of being in such a state for the system was given by the Boltzmann factor. The reason is that if the system is in a state with energy E, it has to borrow that energy from the reservoir. And that reduces the number of accessible states for the reservoir, okay, which makes a higher energy state for the system less likely. Well, you can say a similar thing about particle number. And in fact, it's exactly the same argument as before, except now we keep track of both the particle number and the energy. So if I compare the probability of a state of the system which has n1 particles and energy E1 with the probability of the state of the system when it has n2 particles and energy E2, well, that's given by the degeneracy of the reservoir when it has the total number of particles is n0, but if the system has n1 particles, the reservoir has the rest, which is n0 minus n1. The total energy is U0, and if the system has energy E1, the reservoir has the rest, U0 minus E1. And in the denominator, we have the degeneracy of the reservoir when the reservoir has particle number n0 minus n2 and energy U0 minus E2. Okay? So the entropy is just the log of the degeneracy. So that ratio is the same thing as the exponential of a difference of entropies. the entropy of the reservoir when it has particle number n0 minus n1 and energy u0 minus E1 minus the entropy of the reservoir when it has particle number n0 minus n2 and energy u0 minus E2. And now remember what we did before. We did a power series expansion of this difference of entropies. Question? Because these are particular states I'm considering the probability of one particular microscopic state of the system with N1 particles and energy E1. Yeah, should have written that down. So P of N1 E1 equals probability of one specified microscopic state of the system with N1 particles and energy E1. So there's no system degeneracy. The state of the system is completely specified. The degeneracy results only from the number of accessible states of the reservoir. And so if I do the power series expansion, it's the same argument as before. The zeroth order terms cancel when I take the difference. There are linear terms. The quadratic and higher order terms I'll ignore because they're suppressed by powers of 1 over system size. Okay? So, do power series expansion. In N1, E1, N2, E2, and neglect terms of higher than linear order, because suppressed, I said system size, but of course what I meant was reservoir size, by inverse powers of size of reservoir. So, in fact, those higher order terms that we're neglecting, they arise because for a finite size reservoir, the chemical potential and the temperature of the reservoir are not exactly fixed. So when I take some particles away and some energy away, the temperature changes a little bit, the chemical potential changes a little bit. But we're considering the case in which the reservoir is so big that we can take some particles away, take some energy away without changing the temperature or the chemical potential of the reservoir. Okay? And so this ratio of probabilities becomes the exponential of minus, the minus sign comes from here. We're considering the entropy now as a function of the number of particles. When we differentiate entropy with respect to number of particles, that's minus chemical potential divided by temperature, okay? Well, sorry, I guess that's the next step. I have minus N1 minus N2. Let me write the first step first. D sigma dn with energy fixed. That's from differentiating with respect to particle number. And the minus is because I'm subtracting away particles from the system. And likewise, I have minus the difference in energy for the two states of the system times partial derivative of entropy with respect to energy with particle number fixed. Okay? So that's just from doing the power series expansion. Constant terms cancel. These are the linear terms. Quadratic terms I can neglect. But the derivative of entropy with respect to particle number with energy fixed is minus chemical potential divided by temperature. And the derivative of the entropy of the reservoir with respect to the energy is 1 over temperature. So I can write this, and now I'll put write it as a ratio again with the terms involving n1 and epsilon 1 in the numerator, and the terms involving n2 and epsilon 2 in the denominator. So it's the exponential of n1 mu minus epsilon 1 divided by temperature, divided by the exponential of n2 mu minus epsilon 2 divided by temperature. So this is called the Gibbs factor. It is the Boltzmann factor if we consider no change in particle number. Okay. N1 equals N2. But in general, there's also some contribution to the probability which depends on how many particles the system has borrowed from the reservoir, determined by the chemical potential of the reservoir, just like the cost of taking energy away from the reservoir is determined by the temperature of the reservoir.
Is the Gibbs factor the ratio or is it just one of them?
Well, I don't know. That's a... Yeah, I guess you're right. Normally... Yeah, have it your way. Okay. To be consistent with what I said earlier, the Boltzmann factor, I said, says the probability of a particular microstate of the system with energy epsilon is proportional to e to the minus energy divided by tau. So we've now generalized that to the Gibbs factor. Which now depends on energy and number of particles. And we're saying that probability is proportional to the exponential of n mu minus e over tau. And the reason I wrote it as a ratio is just so I wouldn't have to say proportional to. Rather, the ratio of two probabilities was given by the quantity on the right-hand side. So, as we've discussed before, the Boltzmann factor is telling us that at a given temperature determined by the reservoir, the system is unlikely to be in a state, or at least the probability of being in a state with energy epsilon large compared to the temperature will be suppressed. Of course, that could be compensated by the fact that there are many microscopic states. And if we increase the temperature, then the system can happily be in higher energy states. And the chemical potential is telling us something similar. If we increase the chemical potential of the reservoir, that makes it easier for the system to pick up particles from the reservoir. Increased chemical potential means we're pushing particle number into the system. So like in our previous discussion, we can normalize the Gibbs factor so that we get a probability. Did you have a question? Okay. So like we used the partition function before to normalize things, we'll have a similar sum here. I'm going to write it as script z. Believe it or not, that's a script z to distinguish it from the Latin z I used to denote partition function. So that's the sum over all the states of the system. The exponential of the number of particles in that state times chemical potential minus the energy of the state, all that divided by temperature. So the properly normalized probability of being in a state of the system with particle number n and energy E is the Gibbs factor divided by script z. So it's script z times e to the n mu minus epsilon over tau. And script z I'll call the Gibbs sum. So with that normalization, it is a probability with the property that the sum over states, probability of state, is equal to 1. And as with any probability distribution, I can consider the expectation value of some observable quantity, defined as the sum over states, the value of x in that state times the probability of being in the state. And you remember before we talked about how to obtain the average energy of the system from the partition function. The average energy of the system was tau squared derivative with respect to tau times the log of the partition function. And likewise, if we want to know what the average value is of the particle number, we can find it by differentiating the log of the Gibbs sum. The average value of the particle number, which is the sum over states, probability of the state times particle number in the state, is equal to 1 over the Gibbs sum in the normalized probability distribution, and the sum of n, e to the n mu minus epsilon, divided by tau. So if I differentiate the Gibbs sum with respect to chemical potential, that'll bring down in front of the exponential the particle number divided by the temperature. So that means I can write this as 1 over script z, well, times tau to get rid of that 1 over temperature, tau over script z, times derivative with respect to chemical potential of Gibbs sum with temperature fixed. And equivalently, since I'm differentiating z and then dividing by z, this is tau times derivative with respect to chemical potential natural log of Gibbs sum. With temperature fixed. Well, if I'm interested in describing a system with a particular value of the total energy, like the ideal gas, I can imagine putting the system in contact with a reservoir at some temperature. And then as I adjust the temperature, the energy of the system will change. So if I increase the temperature of the reservoir, the mean energy of the system will go up and up. And if the system is large, the fluctuations around the mean value will be small. So I can get up to some small fluctuations, a desired value of the energy by picking the temperature appropriately for the reservoir. And it's the same thing with the particle number. If you want to study the system when it has some specified particle number, so if we want to know properties of system with particle number n0, choose chemical potential actually I could say with particle number n0 and energy u0, choose chemical potential mu and temperature tau of reservoir so the expectation value of particle number for the system is n0 and the expectation value for energy of the system is u0. Yeah?
So does that mean that the more particles you have in the system, the higher probability it is?
Well, the chemical potential can be negative. So not necessarily.
Okay.
In fact, we'll give an example in a second where it is negative.
And also, can we think of it as if the energy is also dependent on n? So as n increases, the energy can increase.
Well, that's right. So we're summing over all states. Each state has some specified energy and particle number. So, of course, right. I mean, so if you fix the energy per particle, the energy of the state would increase with the number of particles. But the way we're going to use the Gibbs sum, like we use the partition function, is we're going to study the properties of the system by summing over all states weighted by the right probability distribution. And as we, those includes states with an unbounded, in principle, number of particles and an unbounded energy. But in fact, because the probability falls off sharply when the number of particles is sufficiently large and the energy is sufficiently large, we get finite sums. And some finite value for the expectation value of the particle number and the energy. And when the system is large, then fluctuations about mean values are small. Well, the typical fluctuations about the mean particle number actually goes like the square root of n0, but it's a small fractional fluctuation. Similarly for the energy. So when we have a large system, by putting in contact with the reservoir with some temperature and chemical potential, in effect we're studying the system for some fixed energy and particle number, except for some small fluctuations, which become less and less important for a larger and larger system. Actually, I guess I had already given the example of the chemical potential, which we had derived last time, for the ideal gas, just to illustrate that it can be negative. I'll write it down again. Compare. for the system. These are the expected values for the system governed by this probability distribution. Wherever it is, here it is. This is a probability distribution for the system. We use this probability distribution to compute system properties. And so using that probability distribution, I can find the expected value for the particle number of the system and the energy of the system. That's what I mean by n0 and mu naught. Okay? And but physically what's going on is we bring the system to thermal and diffusive equilibrium with the reservoir, and when in contact with the reservoir, the system has a preferred value of the particle number and the energy, and those values are determined by the reservoir's temperature and chemical potential. Those values are n0 and u0. And there will be fluctuations, but they're not very important when the system is large. You had a question.
Yes. Is the chemical potential independent of state?
Yes, because it's a property of the reservoir. It's a property of the reservoir. Okay? So here, when I'm talking about the chemical potential here in the context of the Gibbs probability distribution, here's where it arose. We considered how the number of states of the reservoir changed when the particle number and energy of the reservoir vary. So this is the chemical potential, or actually minus chemical potential divided by temperature of reservoir, and this is 1 over temperature of reservoir. And those are fixed. They're properties of the reservoir, which is huge. And then that determines the probability distribution for the system. So as far as the system is concerned, mu and tau are just constants.
So the n naught and u naught are for the reservoir?
These are system particle number and energy. Right? There's a system, and there's a big reservoir. No matter how big the system is, the reservoir is much bigger. Okay? The reservoir we can characterize by a temperature and a chemical potential. Then particles and energy can be exchanged between the system and the reservoir. Okay? Now, the most probable configuration is going to be the one where the system and the reservoir are in both thermal and diffusive equilibrium. Okay? So what's actually going to happen is that the system will come to a state with the same temperature and the same chemical potential as the reservoir. So equilibrium with reservoir means system temp and chemical potential are also tau and mu. Okay? But as the system picks up energy and particle number, its chemical potential and temperature can change. If it gets more energy, it warms up, right? So eventually, it's going to absorb enough energy from the reservoir so its temperature is the same as the reservoir. That's thermal equilibrium. It's going to absorb enough particles from the reservoir so its chemical potential matches the chemical potential of the reservoir. Now they're in diffusive equilibrium. And that's the most probable configuration of the whole system. And so the system actually has a definite temperature and chemical potential, not quite a definite energy and particle number, except that when the system is really big, the fluctuations around the mean value aren't very important. So it's as though up to those small fluctuations, we've specified the total energy and particle number of the system. Is that okay? Yeah. All right. Well, I guess I was just about to say, or about to write down again, because I didn't emphasize it before, for the case of the classical ideal gas, the chemical potential was tau times log concentration divided by quantum concentration, which actually is the right formula only when n over nq is a small number, in which case the log is negative. The chemical potential is actually negative. Of course, you can always, like other cases where you have a scale for energy, you can always adjust it by a constant. It's differences in chemical potential that really matter. Okay. So, we have a little example of where we can use the Gibbs sum. So we have a piece of semiconductor, maybe it's silicon. And then we add an extra atom. Maybe it's a phosphorus atom. The phosphorus atom has an extra electron. And what we'd like to understand is whether the phosphorus is going to want to ionize, lose its electron, which will then join the other electrons of silicon in the conduction band. So will impurity atom in semiconductor I'll want to ionize. That is, to give up its electron. To the conduction band. Did Gil teach you about band theory in Physics 12b? About block states? Oh, well, anyway. So the point is just that the atom might lose its electron, and then that electron can contribute to the conductivity of the material because it's not bound to the atom anymore. That's what I mean by ionize. So the states that will actually, the electron has a spin. It can be either spin up or spin down. So to get our counting right, we'll take that into account. There are two electron spin states. So there are three states for the impurity atom that I'll be interested in. The one when it's ionized. And I'll just set my zero of energy, so we'll call that the state with zero energy. And I'll call that particle number 0, because I'm thinking of the atom as the system. And when it gives up the electron, it doesn't have any particles anymore. It's empty, right? The electron is gone. But then it can be in what I'll call the neutral state. That means it's holding on to its electron. It's not ionized. And the energy then is lower because there's some ionization potential. I'll call that minus I. So I is the ionization energy, how much energy you need to give the electron to pry it loose from the impurity atom. And that has particle number 1. But there are two such states, of course, spin up and spin down, and they both have the same energy. The energy doesn't depend on the spin, and they both have one electron. So in other words, the electron on the phosphorus atom can be either a spin-up electron or a spin-down electron. So the Gibbs sum, I have to sum over these three states. If we're in the state with zero energy and zero particle number, then the Gibbs factor is just the exponential of 0, also known as 1. And then there are two neutral states, so I'll put in a factor of 2, adding up the contribution from the spin-up state and the spin-down state gives me the factor 2. And then the chemical potential is multiplied by the particle number, which is 1, minus the energy becomes plus the ionization energy, because the neutral atom has lower energy than the ionized atom. So this becomes, the Gibbs factor is the exponential of chemical potential plus ionization energy divided by tau. And so the probability of being ionized, that's the probability of being in the state with zero particle number and zero energy, for which the Gibbs factor is 1. So that's just 1 over z times 1. Okay? So it's the reciprocal of this script z I just wrote down, 1 over 1 plus twice the exponential of chemical potential plus ionization energy divided by tau. So if the temperature is very large compared to the chemical potential and the ionization energy, we consider the temperature going to infinity limit of that probability. Then the exponential just becomes 1. So 1 over z is just 1/3. So in that case, where the temperature is really large, there are three states, and the three states are equally likely. So the two ionized state, or the one ionized state and the two neutral states are all of the same probability, so the probability of being ionized is a third. And when we consider the temperature small, then as long as mu plus I is positive, then the probability of being ionized will go to 0. So the impurity atom is sitting, in this crystal, and it can get ionized because there are thermal fluctuations that can kick it around and knock the electron loose. But those fluctuations become extremely improbable at very low temperature. The temperature is small compared to the ionization energy, and the atom has no choice but to be neutral. But we could also consider adjusting the chemical potential with the temperature fixed. So just as a simple model, suppose we treat the electrons that are free in the material, propagating and contributing to electrical conduction, as a classical ideal gas. Well, the reservoir is the electrons propagating in the sample, or in the material. And imagine that's a classical ideal gas. So we can write the chemical potential as tau times the log of the concentration of electrons compared to the chemical potential, where the concentration is small compared to quantum concentration. Okay. Then the chemical potential, if the chemical potential becomes large and negative, when we have a very low density electron gas, then what happens? Then if we keep the temperature fixed and the ionization potential fixed, and we consider a more and more dilute electron gas, the chemical potential gets very large and negative. That makes the exponential small, and the probability of being ionized goes to 1. So the point is that when the electron gas is very dilute, then there are many places for the electron to go if the atom becomes ionized. And so it can happily gain the energy that it needs to escape because there's a huge entropy gain. Lots of places for the newly liberated electron to go when it joins the rest of them, because there aren't very many there. Okay? So in practice, when we have impurities in materials, usually the electron gas does have a very large and negative chemical potential. And so the impurities typically will want to ionize and give up their electrons to participate in the conduction in the material. Okay. So the next topic we want to discuss is we're going to see the payoff from this chemical potential idea when we talk about the quantum ideal gases. We're going to finally get away from the classical regime and consider gases where the concentration is high enough for quantum effects to be important. And then there will be some qualitatively new phenomena that will be interesting to study. But in the last half hour today, I think I'd like to talk about something else, which is really another application of black body radiation, but an interesting one. And that's noise in electrical circuits. sometimes called Johnson-Nyquist noise. The phenomenon we'd like to understand is at a non-zero temperature in an electrical circuit, let's say you measure the voltage drop across a resistor. Okay? There will be fluctuations in the value of that voltage drop. And they arise because of the thermal fluctuations in the circuit. So specifically, let's consider this situation. We have a voltmeter and a resistor with resistance R. The whole thing is at temperature tau. And I'll explain what this means in a second. But we're going to consider a frequency filter in the circuit. And that means we're only measuring the contributions of the voltage which come from signals which have frequency in a certain band, a certain interval. Well, if we didn't worry about the frequency filter and we measured the voltage as a function of time, what we would see is that there are big fluctuations. And the voltage kind of varies in a wild way, where the fluctuations have some characteristic size. And furthermore, from measurement to measurement, if we measure now and then we measure again a second later and then we measure again a minute later and so on, each time we take the trace for some finite amount of time, we see a different trace every time. They really are random fluctuations, sampling some distribution. And so we can imagine taking such a signal and then Fourier analyzing it. So we get some distribution in frequency space or some history or some probability, some weight for each one of the frequencies. And then add up the contributions only from the frequencies in a certain band. Now, band just means an interval in frequency space, say from frequency f to frequency f plus df, where df is some small increment in the frequency. And then we look at the signal, the filtered signal, by which I mean the contribution to the voltage as a function of time that only comes from frequencies in this band. So consider at some fixed time the filtered voltage as a function of time. And then we make the measurement many times. So each time we get some function of the voltage as a function of time. We Fourier analyze it. We look at the contribution in a certain frequency band. We look at the corresponding voltage as a function of time just coming from that band. And at some particular time, we get this filtered value of the voltage. We do it many times. We get some probability distribution for this quantity. Okay? And what we find, if we take expectation values for that probability distribution, is first of all that the mean value of the voltage is 0. I'm not applying there's no battery in the circuit, so the voltage has no reason to prefer positive values or negative values. It's fluctuating around 0. But we can also characterize its mean square fluctuations. If I look at the filtered value coming from a certain frequency band of v squared, it's given by 4 times the temperature, the resistance, times the width of the band. So just make sure the notation is clear. This is the resistance. This is the bandwidth. And of course, this is the temperature. That's Johnson noise, yeah.
Question. So if there is no battery in the circuit, what does that mean?
Well, it's actually fluctuating around 0.
No, like what does that symbol mean in the circuit?
Oh, yeah, sorry. That's a voltmeter. Yeah, good point. We're just measuring the voltage as a function of time, not a voltage source.
Why is there any voltage at all?
Well, we're about to see. I claim it's coming just because there are thermal fluctuations in the circuit.
Oh, cool.
Yeah. So this is the empirically observed phenomenon that the fluctuations in the voltage are proportional to the temperature, the resistance, and the bandwidth. Okay, and in fact, with this numerical factor 4, Johnson discovered that, and Nyquist explained it. And so we'd like to understand his explanation. And actually, we can make the derivation a little easier if you'll allow me to use a little bit of electrical engineering lore, which is this. If we consider a transmission line like a coaxial cable, and then we terminate the transmission line, in this case with a resistance, if we match the impedance of the transmission line with the impedance of the circuit terminating it, the resistance, then all the power coming down the transmission line will be absorbed and dissipated in the circuit. There will be no reflected power. That sound like something you've heard before? Okay. So all power is absorbed. So the power that's coming down the line, that's electromagnetic radiation being carried by a waveguide. And what we're saying is that when there's impedance matching, the resistance is a black body. It's absorbing all the radiation that's incident on it with no reflection. Okay? So when there's impedance matching, a resistor is black body. Remember, that means it absorbs all incident radiation. So if we're in thermal equilibrium, the resistor is in equilibrium with the transmission line, then the amount of power coming into the resistor at the end of the transmission line matches the power that the resistor is dissipating. Okay? So dissipation in a circuit matches power transmission line delivers to circuit. So, what's that rate of power coming off the transmission line? Well, the transmission line is really just a cavity with radiation in it. So think of it as a one-dimensional cavity with length L, so that the wave numbers for the modes in the cavity can be written as pi n over L, where n is a positive integer. Okay. Correspondingly, the circular frequencies of those modes can be written as the speed of transmission in the transmission line, let's call that v, times the wave number. So that's pi times v divided by L times the integer n. Now, each one of those modes in thermal equilibrium at temperature tau have an expectation value of the energy stored in the mode, which is just given by the Planck distribution. In other words, we know it's h bar omega, the energy of a single quantum, times the expectation value for the number of photons occupying the mode, e to the h bar omega divided by tau minus 1. Let's suppose that the circular frequencies are small compared to the temperature. Let's consider the high temperature limit, in which the temperature is large compared to the energy of a single photon. So it's the classical limit of electrical noise. So this, remember, is just tau when h bar omega is small compared to tau, the classical limit. So if we treat all the modes classically, there's energy tau in every mode. So what's the energy per unit length in the cavity? So it's energy tau per mode divided by the length, as I'm computing the energy per unit length, and then a sum over modes. That means a sum over n over non-negative values. So if we consider the transmission line to be long, I can replace that sum by an integral. That is, I can think of the sum over n as being like L over pi v times an integral over omega. Tau over L times L over pi v integral d omega from, well, in principle, it's only over non-negative values up to some maximum wave number. But we're only going to be considering the fluctuations in a certain bandwidth. Actually, let me write this in terms of an integral over frequency, because that's the notation I used before. So this is tau over pi v, and then I get a factor of 2 pi if I write as a frequency integral instead of a circular frequency integral. So it's 2 tau divided by the speed times frequency interval. But what we're interested in is the rate at which power is coming off the end of the transmission line. We have this cable, and while half of the modes are traveling to the right and half of them are traveling to the left. So the rate at which power is being emitted at either end is the speed v it's equal to 1/2 because we're only interested in the modes that are traveling in the direction to the right instead of to the left, times the energy per unit length times the speed at which the signal is being emitted from the end. It's just like our earlier calculation in which we related the energy per unit volume in black body radiation to the rate at which energy comes out of a hole in a cavity. But this is just the case of a one-dimensional cavity. So that means the power is just temperature. So here's our expression for U over L. Here it is. And then the 1/2 gets rid of the 2. The V gets rid of the 1 over V. So it's just temperature times integral dF. Okay, but we're looking at the filtered power because we're only interested in the contribution to the dissipation and the resistance at the end coming in a certain frequency interval. Okay, so we're going to integrate F over the bandwidth to get the contribution to the signal coming from power in a certain frequency window. All right. The power is the resistance times I squared. But we're considering I squared in the specified frequency band. And then we're going to average I squared. And that is going to be tau dF. Okay, where this is the bandwidth that the filter allows to pass. Okay. And now there's a tricky factor. I have to relate the current to the voltage. Okay, but actually there are two contributions to the impedance. One is the resistance in the circuit itself, and the other is the matching impedance of the transmission line. Okay, so the relation between the current in the circuit and the voltage is that the voltage is equal to 2R times I, because we have to include the impedance of transmission line as well as resistor. So that means if you consider the filtered voltage signal, its fluctuations are 4R tau dF. And that's Nyquist's formula. Yeah?
What's the reason that the 2R are equal?
Well, the reason for the 2R is that we want to know
Shouldn't the R outside the arbitrary? Just like what
well, I mean, they form a
the resistance there depends on the
Yeah.
And the other R is just whatever, like external impedance you put in with the voltmeter.
Yeah. Well, I think it's just that there's a voltage, and it's really driving two impedances that are in series. So we have to, because the power, is coming from the. The way the current is determined by the voltage, which is driving a circuit, which consists of the resistor, which is dissipating the power, and also the transmission line. It is pretty confusing. So that's Nyquist's formula. And really what it's telling us is that if we want to measure a voltage, we'll have to integrate the voltage for a while in order to overcome the effects of the noise. I put more details in the notes about this than I guess I'll have time to do on the blackboard. But why is it called white noise, by the way? Maybe I didn't tell you it's white noise. This is called white noise. What's white about it? Right. So it's completely flat spectrally, just like white light, which has no preferred frequency. And so having contributions to the voltage squared in each frequency band, we can think of them really as being independent fluctuations in each frequency band. And then if we integrate a signal over some time, we have to add up the contributions coming from all the different frequency modes. And the fluctuations will grow. If I look at the voltage squared, the fluctuations of voltage squared grow linearly with the time. Okay? So another way of saying what's happening with white noise is that you can imagine dividing the time up into intervals, and there are independent fluctuations, uncorrelated fluctuations in each of these successive time windows. The way I drew it wasn't very uncorrelated, I guess. But say we have time windows with width delta, and in each window the voltage varies independently of the voltage in the other windows. Correspondingly, if you look in Fourier space, each one of the Fourier modes has independent fluctuations, and with fluctuations which are independent of frequency. So what it means is that if you want to see a voltage signal, you have to average it for a while. Okay? And the Nyquist noise, which has the dimensions here of a volt squared per hertz, that's what the mean square fluctuations of the voltage look like. So the fluctuations of the voltage itself goes like the square root of that, or volts per root hertz. And so what it means is we have to integrate for a while and average the signal in order to see a signal which isn't completely swamped by the fluctuations. So if there's actually some non-zero voltage, the fluctuations may be large, but they tend to average out. So if I look at the average voltage as a function of the time that we integrate, the fluctuations tend to average out. And if we integrate long enough, we can measure the signal. So to get an idea of what the numbers are, remembering that I can write the Boltzmann constant as 1.4 times 10 to the minus 23 joules per degrees K. Suppose I consider a resistor which is 50 ohms and a temperature of 300 degrees. Then the size of the fluctuations are something like a microvolt squared. If I choose a megahertz bandwidth. And so it means I need to integrate for, a time like a microsecond in order to see a microvolt signal at a temperature of 300 degrees for a circuit which has a resistance of about 50 ohms. Now, we made this approximation that we considered the temperature to be large. And in most cases of interest, that's a good approximation. But if you consider sufficiently low temperatures in high-frequency circuits, that approximation might break down. So specifically, if the frequency is about 1 gigahertz, you can ask at what temperature will h bar omega become comparable to kT? And the answer is it's about 40 millikelvin, so much less than a degree. But actually, experiments for the last 10 years or so are often done at temperatures in the range of tens of millikelvin for circuits which have gigahertz frequencies. So the quantum effects on the noise are an important part of modern-day experiments for studying quantum effects in devices where, for example, one is trying to do quantum computing. So the Nyquist regime, which applies to circuits in everyday situations, doesn't necessarily apply to state-of-the-art experiments at high frequency and sufficiently low temperature. Okay.